is lesson 3.1, solving one-step equations. You should be on page 134. Let's talk about an inverse operation first. An inverse operation are two operations that undo each other, like addition and subtraction. When you do an inverse operation on each side of an equation, you produce what's called an equivalent equation. An equivalent equation are two or more equations that have the same solutions. Now remember, that term solution from Chapter 1. Solution means that you can take a number, plug it into the variable, and it makes the statement true. Now, first of all, I would get those terms in your notes, but here would be a simple example of what inverse operation and equivalent equation would look like, okay? Let's take a simple problem like x plus 5 equals 7. I'm sure as you look at that you already know the answer, but let's actually work it out. Now to solve the problem and get the proper answer, we would have to take away 5 from each side because, think about it, if we're adding 5, the inverse would be to subtract 5. That's the opposite thing to do. So I'm going to subtract 5 from each side. I get x equals 2. Now I think most of you knew that the answer was 2 in the first place. But now, this term equivalent equations, let me take a red marker and let's just check. If I plug 2 in for x for this little equation here, you understand that 2 is a solution. It makes the statement true, but then go up here and plug a 2 in for x. Do you see how that makes that equation true? These two equations that I'm arrowing are now equivalent because I could put a 2 in either one and it makes the statement true. If you are doing inverse operations properly, each new statement, each new equation will be equivalent to the one prior. There are two properties then we would need to know, and we just used one of them in my prior example. There's first of all an addition property of equality, pretty basic property. When you add the same number to each side of an equation, it should produce an equivalent equation. I'm going to draw a quick little picture. I like doing this every year, and I'm sure you've seen in science class a balance scale. Okay, a balance scale looks, and sometimes you see this in front of like a courthouse or maybe a place of justice where you have a picture that looks like this with two balances and you see two plates, one on each side. The scale is balanced right now. An equation works just like a balance scale. So in that prior example, when I had x plus 5 on the left, my plus isn't showing up. Let me put it in a different color. X plus 5 on the left, and I have 7 on the right. Okay? If I take away 5 from each side, and I have x equals 2, like I had in my prior page example, the scale is still balanced. My equal sign is still true. Okay? The addition property of equality ensures that my equal sign will be still valid. Like, for example, take x minus 3 equals 8. Right now, it's kind of like having a balance scale. Let me draw one in. Right now, both sides of my scale are balanced. If I add 3 to each side, which is using this property, my scale is going to remain balanced. X would equal 11. If I put 11 in for x in this equation, it's equal, but look what happens if I put 11 up here. 11 minus 3 equals 8. Both of these equations are equivalent. My balance scale always stayed balanced. This concept, this property allows me to keep my equation valid if I add the same amount to each side. There's also a subtraction property of equality. It says the same type of thing. If you subtract the same number from each side of an equation, you will produce an equivalent equation. Here would be an example of that. Something simple, x plus 3 equals 12. If I subtract 3 from each side, which is the inverse of adding 3, that's where this term inverse operation comes from, do you notice the plus 3 minus 3 cancel? I'll have x on the left of the equal sign and 12 minus 3 equals 9 on the right. And you notice now I have two equivalent equations. I'm putting an x next to each. If I put a 9 in here for x, I get 9 equals 9. That's true. And if I put a 9 up here, 9 plus 3 equals 12, that's true. In other words, my balance scale, I'm going to kind of draw it in here, this plate equals this plate, and down here, this plate equals this plate. The scale stayed balanced the entire time. Let's do a sample problem. X plus 7 equals 4. So I wrote the problem. Now, I want to get rid of plus 7. The inverse would be adding 7. I want to get x by itself. So I'm going to take away 7 from each side. The 7's on the left will cancel out of the equal sign. So x on the left would equal, well, 4 minus 7 would be negative 3 on the right. And these are equivalent equations right now. Okay? My first equation is equivalent to this equation. If I put negative 3 in for x down here, I get a true statement, and if I put a negative 3 in for x up here, I still get a true statement. These two equations are equivalent to each other. The way I'm writing these out is called the vertical format. I would highly recommend the vertical format. It's less writing. And I know everyone watching this video right now likes less writing. If you want to use the horizontal format, that's okay, but you're going to have some more writing. Do you notice in the horizontal format that you wrote the problem, you had to rewrite the entire problem here, and then show that you're adding 12 to each side to get that same answer of 15. Where here, you just wrote the problem, put plus 12 on each side, and you get 15 right away. There's less writing using the vertical format. That's what I would encourage you to do. If you do the horizontal format, I won't mark it wrong, but here's one thing that we have to know. Either way, and maybe I should highlight this in a color, or maybe I should circle it in red, either way, you will show your work if you want full credit. If all you do is write the answer, I typically make these problems worth 3 points, and maybe I should write that on here. Typically, I make the problems 3 points, and here's how I grade it. It's 2 points for the work and 1 point for the answer, okay? 2 points for the work, 1 for the answer. So if you want to write the right answers down, I can give you a 1 out of 3 on every problem. I want to see your work. I want to see how you're getting the answer. And the work's important because not all the problems will be this easy, and this method that I'm showing you, as the problems get more difficult, we need to know this. What happens if the problem isn't addition or subtraction? Let's say it's multiplication or division. Now, multiplication and division are inverses. They're inverse operations. So, again, we have two similar properties. The first one is called the multiplication property of equality, and it simply says what you've already seen before, that if you multiply each side of an equation by the same amount, you will produce an equivalent equation. Here would be an example of that. X divided by 3 equals 8. The inverse of dividing is multiplying. So I'm going to multiply each side of this problem by 3. Can you kind of see that my balance scale is right here? You know, my two plates are equal right now. I'm multiplying the same amount to each plate, so the plates should stay equal. Does it make sense that divide by 3 times 3 cancels? I have x on the left, and 8 times 3 is 24. I'm getting 24. Let's check that now, okay? If I take 24 and plug it in here, 24 certainly equals 24. If I take 24 and plug it in here, 24 divided by 3 does equal 8. So I have equivalent equations. The same thing works for division. If I divide each side of an equation by the same amount, I will produce an equivalent equation. That's called the division property of equality. It would be a sample. 3x equals 18. I want to get rid of the times 3 from x, so I'll divide by 3. That's the inverse. Times 3 divided by 3 cancel out. I have x on the left, and 18 divided by 3 is 6 on the right. And can you see how when I draw my balance scale in here, my scale was balanced to start, because these were equal. I divided the same thing on each side, which shouldn't change my scale, and it doesn't. X would equal 6. Now, I have two equivalent equations. If I plug a 6 in here, 6 does equal 6, and if I plug a 6 up here, 3 times 6 does equal 18. I have equivalent equations. Let's try it. Why don't you stop the video and try 1 and 7. Show your work. Number 1, there's the problem. The inverse of adding 7 is to take away 7. You should have ended up with y equals 3. These two equations are equivalent to each other. If I plug a 3 in here, I get a true statement. If I plug a 3 up here, I get a true statement. This other problem, I'm going to have to divide by 6 to get rid of the times 6 away from w. So I divide by 6. My 6's cancel, and I have w on the left would equal negative 54 divided by 6 is negative 9. One other look that we have to be aware of, or a couple other looks here, in this problem, I'm dividing t by negative 3. Well, what do I do to get rid of division? The inverse of division is multiplication. So I'll multiply each side of the equation by negative 3. So the times negative 3 divide by negative 3 cancel. You can see I slashed them out. I got t on the left, and 9 times negative 3 is negative 27. Can you see how my balance scale is staying balanced? My equation was equal to start, and when I multiply each side by the same amount, I still have two equal amounts. If I put negative 27 in here, I get a true statement. And if I put negative 27 up here, I also get a true statement, because negative 27 divided by negative 3 does give me 9. Always check your answer. You know, when you get an answer, it should be easy to plug it back in and check it. Really, even on a quiz or test, you should already know before you turn it in whether you have the problem right or not. If you take the time and plug your answer back in to the original statement, it has to be true. If it's not, then that's a red flag. There's something wrong if you are taking your number, plugging it in, and it's not working. Always check your answer. Okay? And to wrap this up, you will see this situation pop up. I'll do number 13. It's a similar problem to this example. And let's do the work here. 5, 6, w equals 10. Now, I like to teach the problem this way. Since we're multiplying 5, 6, and w, we ought to be dividing each side by 5, 6. Yes, I know that looks a little strange, but it's the truth. To get rid of times, you divide. So when I divide by 5, 6, times 5, 6 divided by 5, 6 cancels. You can see that where I cross those out right here. Cancel out. W on the left would equal 10 divided by 5, 6. You are allowed to use your calculator in this chapter. So just make sure when you type it in, 10 divided by parentheses 5 divided by 6, you ought to be getting 12. Now, when you look at my work, you might be looking at the example in the book and saying, wait a minute, that's not what they did. I am doing the same thing. I'm dividing by 5, 6, but now let's talk about why the book did what it did. Here's why. Do you remember that dividing is the same as multiplying by the reciprocal? So I can do this problem in two ways. I could divide by 5, 6, which is what I did here, or here's the other way you could do it, and this is what the book is showing you. Oops. And here's what the book is showing you. That same problem, instead of dividing by 5, 6, we could multiply by the reciprocal. I'll multiply each side by 6 this. These are inverse operations. So times 5, 6 times 6 this cancels. I'll have w on the left, and 10 times 6 this would give me 12. It doesn't matter if you divide each side which I did in my prior slide, or if we multiply each side by the reciprocal, which is what this is showing me in the book. They will have some word problems for you to try at the end of the practice, and those word problems, as you notice here, will set up into one-step problems where you'll have to use an inverse operation to solve. I'm going to stop the video there. If you have questions, make sure you ask in class.